Okay, this is 1.3 exchanging data. So I'm going to go through these 4 sections for you and let's go. So compressing files is about making a file smaller to increase the speed and lower the bandwidth used when sending across a network or the internet. It's also about making a file take up less space on the storage, secondary storage or whatever. So there are 2 types of file compressions which use different algorithm types. One is called lossy and one is lossless. A lossy compression technique will compress files, but it will lose some of the data. So when you decompress the file, it is not the original file. Think of it as crushing a can in your hand and then uncrushing it. It'll be similar to what it was, but it has been forever altered, although obviously a can could be repaired, but a file cannot. So it's only really used on multimedia files such as sound, video, images, and music. Okay. Lossless compression compresses the file and doesn't lose any data. It does an algorithm where after you decompress it, it is mathematically the same. This can be used on any file type, but will generally give less compression than lossy compression. But remember, lossy can only really be used on multimedia files. It doesn't mean all multimedia files are compressed lossy. It's possible some scientific or medical data would need to be so accurate they would compress it lossless. PCX and a few others are lossless compression methods that don't lose any data on images and things like that. So, but you can only use lossy really on media. So let's have a look at a lossless compression called run length encoding. This is a very basic compression that looks for repeating data. So here we have some data. We have 1 0 followed by 4 1s followed by 3 zeros. So I could represent that in 6 digits rather than 8. I could have 1 0, 4 1s, and 3 zeros. And so you see I've compressed these 8 bits down to 6. So lossless compression, if I was to rewrite that out, if I write out 1 0, 4 1s, and 3 zeros, I'm getting exactly the same data. Not something similar, exactly the same. If I compress it and decompress it 1 billion times, assuming no errors, I should get the same file. But obviously you generally don't get as much compression with lossy as I mentioned before. And as you can see here in this row, I've deliberately done it so that you get no compression. And here, in fact, it would increase the file size with this method because there's not enough repeating data. But just remember, this is a very simple method, run length encoding. There are other ways to do it. You could have patterns you could look for and things like that. And there's much better techniques that are harder to explain and you don't need to understand them. You just need to get that this is a version of compression called run length encoding. So another way you could compress something losslessly could be used some sort of dictionary-based technique. So I have created this terrible nursery rhyme because I want to get copyright struck. I'm not going to read it out. And I could then, give numbers to a new line, one to an A, one to cat, and then I could simply, this would be 1, 2, 3, 4, 5, 6, 0 for new line, and then 7, 8, 9, lowercase coat. Well, I've got an uppercase coat there, but we'll assume that's a typo. But you get the point. So the problem with this, obviously, is that I would need to include this table with the files. So if the file wasn't very long, it might get bigger, actually, and probably would. But there is a possibility I could say actually have a dictionary on the computer before, like stored locally, and use the same dictionary in all of my compressions, and then, and it could be used. So this is another technique you could use. It doesn't have to be words. These could be sort of repeated data. Like here, we could allocate sort of numbers to these different blocks. We keep getting 4 blocks of 1, so maybe we allocate 6 to that. And other numbers like 0, 1 could get a special number like 7. So we have 0, 6, 0, 0, 0, and then whatever. And then 6 would be 4 1s. And if there's any other numbers, we could do some other patterns and things like that. So that's what dictionary-based a dictionary technique does. Okay. So let's look at encryption. Okay. So this is the act of transforming data from one form to another to stop unwanted third parties from being able to read it, even in the case of a data breach. So we've got some keywords, which I'll just read out quickly. We've got the plain text, which is the original file. We've got the ciphertext, which is the encrypted message or file. We've got the cipher, which is the method or algorithm used to encrypt the data. And we've got the key that's used to unlock the message. So we're going to look at a terrible substitution cipher called the Caesar cipher. And this is a very, very basic form of encryption where you simply shift letters down the alphabet. So we could agree to have a shift of 2. It's named after Julius Caesar, but I won't go through the history. It's probably not true anyway. But yeah, so if I wanted to, so if we had a shift 2 method, and I wanted to encrypt the word hello, then the H would go down 2 letters to be J, the E would become G, the L would become N's, and the O would become Q, which I think I actually do on this one here. Yes. So this has been shifted with 2 down, and you would need, of course, to shift it 2 back to do it. You could do different shifts, of course. Maybe 8 might be slightly more complex. But the reason this technique is terrible, apart from being just trial and error of get it, is that you have this thing called a frequency analysis, which can look for the most common letters being used. So this is a frequency analysis of sort of the dictionary. Obviously, it could change depending on the set you give it, but this is roughly correct. So E is by far the most used letter, followed by T, and then A, and then O, and I. And so, obviously, if we have a long enough message and we're shifting it down, if I suddenly see G shooting up here, I'm thinking they've shifted that along by 2. And so it's quite easy. There's many websites actually where you can give some Caesar ciphered text, and it will, with not trial and error, it will use it. It can do trial and error, of course. There's only 25 options, but it can do it by frequency analysis and predicts the code for you, which is quite good. So anyway, it's only a sort of joke for encryption, really. It's not really used, but it lets you understand the concept of how encryption could work. So what's one that could actually be used? Right, well, this is one called the Vernam cipher. Now, I'm going to have to go through this a bit slowly in a minute, so bear with. So Vernam cipher is an uncrackable, and it literally is because there's no pattern to it, because the keys are only used once, and I'll get to that in a minute. It uses a one-time only pad, which must be longer than the message itself, or equal to. Both parties use the same pad to decrypt and encrypt the message, but once it's used, the pad will be binned. Now, an XOR operation is then performed using the original text. Now, this is best done by example to show you what I mean. The biggest problem with the Vernam cipher is the pad must be truly random and only ever used once, but it's virtually impossible to create a truly random thing. You can do it with atoms and stuff and radiation decay and things like that. But I suppose how random's it got to be very safe? I don't know. But if it is completely random, then there is no way to crack it, because it's literally every time you do it, it's using a different method, a different numbering system, really. So there's no way to crack it. Anyway, I will just show it. I'm just going to pause momentarily. Right, so if I go here, this is my original message, okay? Hello, capital H. That's the ASCII values or the Unicode values, whatever you want to call it. And so at this point, obviously, that's what I want to send in the file. So I created a Vernam pad randomly, but obviously I did this. It's not random. It's not actually randomly generated. I just randomly press keys, but also I'm human. I can't do random. So what do you do with that? Well, what you do is you perform an XOR of these two numbers. And if you've forgotten what XOR is, I'll just quickly bring it up. So this is 72 along the top here. This is 57. And so we end up with, you do an OR, but exclusive OR. So this would end up with, oh, no, because it's double 1. And then we'd end up with that. 00011 0001, which is 131. Yeah, which it is. So that's 131. Okay. So now this is actually what would be sent. Right, that's the message that would be actually output to the person. You would be getting that. So I've started with this, I've XOR'd it with that, and the thing with XOR is if you do it again, you get it back to the original. So what this person's got to do is XOR this with the pad again. And if you XOR that again with this, because the way XOR works, you will get the original message. So this is the original message back. So the person at the other end would XOR it again with the pad. So you XOR it with the pad to encrypt it, they XOR it with the pad to decrypt it, and then they've got the message. And the reason it's uncrackable is because if this is truly random, you can see these letters are the same, but we have no idea what these numbers will be here, because they're solely based on the numbers here. And if these are random, then it doesn't matter what these are. Like, it doesn't make any difference. If these are completely random, they're going to change these massively. But of course, it's one use only. And at some point, you've got to get, how you're going to get the pads to the person. So the Vernon cipher is not a, not a solution for everything, but it could be used in some sort of military, where you literally deliver something, in a box, sealed. I don't know, some sort of code. Anyway, that's what a Vernon cipher is. So let's move on. So non-random keys, okay. Any cipher that doesn't use truly random key can be hacked, but the difference is time. Yeah, that's about getting random numbers. You can look it up, white noise, which is like audio background, and radioactivity decay. And this is something they've got to think about with quantum computers in the future, because there's, obviously by the time you watch this, it may be true, but they're trying to develop quantum safe encryptions. But I just heard of one the other day that won an award. It got into the top 6. There's actually a place of it's quantum safe. It's the next, and it got hacked in an hour on a normal computer, not even a quantum computer. So, and that was really far down the this is going to be the solution list. So it's quite worrying that when quantum computers come out, what they do, because they will do things very fast. Obviously, if you want to know more about quantum computers, I could leave a link or something. There's many great videos out there. And it's very interesting. But anyway, so that's non-random keys. If it's not random, in theory, it can be hacked. So what's symmetric versus asymmetric? Well, they are opposite words. Symmetric means that both parties use the same key to encrypt and decrypt the message, just like in the Vernon cipher. It must be kept a secret, and the key exchange must happen, and this needs to be planned carefully. So the Vernon cipher was an example of a symmetric key exchange. Asymmetric is where there is two keys, one used to encrypt it and one used to decrypt it. And it's impossible pretty much to get the one key from the other. But you just need to be careful though, because someone could use a public key to try and pretend they were someone else, because if the key is public, they could try and pretend like it was coming from someone else. And we prevent this with a digital signature. I'm going to explain asymmetric keys in a minute in much greater detail. So if that wasn't a great explanation, literally I'm going to go into it now. So older systems, right, used to have one key to encrypt, one key to the same key to decrypt. But imagine we had this, okay? Imagine we generated a pair of keys. Let's call them key A and key B, and they're linked, and you generate them together. I'm going to show you one that I've just generated. I can click it here. Let's generate a 1024-bit. So this is a private and a public key. They're linked. I need, that's my one. That's my public one. That's my private one. Okay, I'm going to show you in a minute. I'm actually going to encrypt some stuff in a minute and then show you the use of those things. So the point is, how these work is, now at the moment that says public and private, but just for the minute, just think of them as key A and key B, right? Because you pick which one, doesn't really matter. Either of those could be my public or private. So basically, things encrypted with key A can only be decrypted by key B. Things encrypted with key B can only be decrypted by key A. And this is brilliant. So what you then do is you pick one of them. Let's say pick key A. And that's your public key, and you keep key B private. So you create these pairs, just like I did on some website like that, or with a piece of software. And you've now got a pair, and I can release one to the public, but keep one private. Now you might think, what's the point of that? Why would I want to give out one of the keys, right? Well, it allows you to do two things. People can send files to you safely, right? Because what they can do, they can use your public key that you have literally released to the public. That's why it's called a public key. You put it on the end of your Twitter handle or whatever. Anyone can encrypt a file with that, knowing that only you can decrypt it. So if they want to send you something, but they want only you to have it, right? They use your public key to encrypt it, and only you can decrypt it. They can't even decrypt it with the public key, obviously, that's public. It's only one way. Once the public key has encrypted it, it can't be decrypted with that key. Okay, you can only generate, it's one way. So that means that someone can send you a file and hope, theoretically, they know that only you can get access to it. And the opposite is true. Okay, you could encrypt your file here, so people can be sure you made a file. So let's say I want everyone to know that I made a file. I could even put it on my website, but my website could get hacked, and you want to make sure, actually, is that the real file that Bob made, in this weird example, or whatever? Well, Bob could use his private key to encrypt the file, put it on his website. When you download it, you use Bob's public key, which you've kept, to decrypt it. If you can decrypt it, then you can be fairly sure that Bob created it, because the only way he can make a file is if he had the private key, or someone else had the private key. But obviously, if he gives away his private key, what are you going to do? So the point is, you can use the system to know whether someone has actually sent or created a file, right? And that's basically what it is. It also encrypts it, of course. So they're the two situations. Someone can send you a file safely using your public key. You decrypt with private key. Or you can encrypt something with your private key, send it out to people, and if they can only decrypt it with your public key, then they can be sure that you created it and it is the original document, not been changed or whatever. Okay, so it works in both directions, and that's quite useful. And it is useful for something in a minute called a digital signature, which we're going to talk about, but I need to introduce you to something else in a second called hashing. And yes, so because, for example, what you could think is, let's say I've said here that you could send a document or a file, and that's fine if the file is small. But what tends to happen is it's quite cumbersome to encrypt and decrypt this, and quite slow. And if the file was, say, 1 gig or 10 gig, like, you're just not going to encrypt 10 gig of data. It would take ages, or it could, whatever. So what they do is they create something called a hash. Now, what a hash is, a hash is generally a one-way encryption, right? So, for example, if you have a password, it will turn it into that. Like, it's a one-way encryption, a one-way thing. It turns your file with an algorithm into something like this. Okay, that's generally what hashing does. You hash passwords, and then if I wanted to check if someone's password was right, what I would do is, say I'm Netflix, and I've got your username and password. I have your password stored like that, not like that, right? Because obviously that'd be terrible to store it like that. And also, Netflix don't know your password; they know this. They can't get your password from this, well, not easily. It would take a long time. But what they can do is, if you give them this and they hash it and it turns into this, they know that you gave them the correct password. So that's what hashing is. It's sort of like a one-way check, okay? And you can use it to see if a file has changed as well, if you hash a whole file, which I'll talk about in a second. But they don't hash the whole file, they do a clever thing. So that's what hashing is. It's turning sort of normal stuff into a set, normally represented, it's binary, but obviously it looks hexadecimal. It's one way, and we use it to check things like passwords. But what you can do is get the hash of a file. Now, I'm just going to do this in Windows 11. I think I've got to do PowerShell. Right, so I've got to do PowerShell, which is PowerShell. Got to run it as admin because I need admin access to do a file hash. So let's go to decode on. Right, get a directory. What's here? Got some rubbish there. Look at this: fitness videos, ebooks, anime. What a cool person I am. Right, so let's go to my D drive and then create a file. I'm going to create a text file called, I call it something small, text.text. Right, and I'm going to go like, hello, this is a hashed file. Well, this will be hashed. Right, okay, save it. Right, so now I've got that file there. So if I go back to PowerShell, do a directory, I'll get text.cover, text.text, right? So now I want to get the hash of that, and I can't remember how to get it. Because normally I would use a program to do it and not just use PowerShell. I think it's called, what do I type? Sorry, apologies. It's get file hash, right? So if I do get dash file hash, oh no, get file hash, and then space and text.txt. Yeah, there we go. Right, so I've got that hash. So what it does, it creates a set length output. This is probably using something called H446, probably, but don't quote me on that. Although I've just seen it says it right there, so I'm an idiot. But yes, so basically it's going to create a 256-bit version of the file. that's not unique, because obviously it can't be unique if the one with the file is smaller than 256-bit. But let's say it's a 10 gig file. It would still create a 256-bit representation of the file. That is pretty unique to that file, right? So if I get that, it's always going to be the same. But if I change the file, even by 1 bit, and then go back, the hash will be different. And so you can really closely be sure that if I send a file to you, if I put a file online, like this text file, and then I email you this hash, right? And then you get this file, you can check the hash. There's probably other ways you can do it. Probably can do it with properties. I don't know what, I probably didn't need to do all that. I probably could have just done this. Does it have the hash here? No, but you could then do this, check the hash, and then say, right, does that hash match that? It does. That's the file. Brilliant. So that's what hashing does. It will sort of give a 256, in this case, although you can do different numbers, just to be clear. And so this is really useful for a digital signature, because what you can do is you can take the file, like the Word document, right, that I'm sending to you. Oh, let's say I'm sending you a video. It's 10 gig, right? So a digital signature, by the way, is a way of saying I made this document. It's not actually a signature like draw. So because it's cumbersome to encrypt a whole file just to check for the sender, right? What you can do is hash the file. So I hash the file, I get that, and then I can use my public key, your public key, sorry, the person I'm sending it to, or whoever, my private key or whatever, to actually, sorry, if I'm making this file and sending it to you, right? So I'm the person who holds the keys. I'm Bob before with my public and private key. I hash the file to give myself a 256-bit thing of it. I save that as some sort of text, and I encrypt it with my private key and send it along with the file. So now you have got the file and my an encrypted text. You decrypt the text with the public key. So if you can decrypt the text for the public key, then you know I made it because I used my private key. Then you can check that hash next to the file hash, and if they match, you can be relatively sure that I sent the document because I encrypted it with my private key, and the document hasn't changed because obviously if you change the document, the hash won't match. And so that's the idea behind a digital signature. Okay. But yeah, there you go. So that's the concept of it. I hope I explained it well enough. It is a little bit fiddly. But yeah, there you go.